And we can now move toward the last presentation about Voronoi filters for simulation enrichment. And the authors are Juan Casafranca and Miguel Otadui, and they are again from the Universidad de Juan Carlos in Madrid, as well as in the company CEDI, who works in 3D fashion design. Yeah.
Oh, okay, so thanks for the presentation. I'm Juan Casafranca, and I'm going to show this work, Voronoi hierarchies for non-conforming simulation refinement. So what we try to simulate with this work is two kinds of simulations: multi-resolution simulation, simulations that have different size of elements throughout the LMS, and multidimensional simulations that have different kind of elements of different dimensionality. So first of all, multi-resolution simulation, in mesh-based simulations, the accuracy of the simulation is determined by the refinement of the underlying mesh of the underlying mesh. So if you want to achieve a good simulation with a lot of details, you need a lot of elements. So for example, instead of putting a lot of elements all over the place, you can do like they do in this paper in Axi, that they dynamically introduce elements where they need it. The issue with this is that it's very suited for triangle meshes, but it's difficult to use for example, in volumetric meshes. Also, if you want to simulate an umbrella, you just can't use a single type of element like a cloth, mainly because the umbrella is made of some parts that are 2D, some parts that are 1D. So you need different kinds of elements. So what we are going to do is use some kind of constraint simulations that we are going to mix two non-conforming meshes to represent those discretizations. Of course, we are not the first ones to do this. Some years ago, Drax already proposed using two different 2D meshes. Basically, they do that for controlling animations, but it was only used for 2D. I mean, only for surfaces. Also, in multifarious hierarchies of mechanical multifarious hierarchies, they basically propose using several discretizations representing different parts of the mesh. For example, in that fat type, and they can use rigid bodies or a linear length scheming for the arms and legs and all that, and then use FTM, for example, with different resolutions for the stomach. The issue with that is that they needed to compute some constraints that were very difficult to update and during the simulation. And also, in 2 years ago, we proposed using triangles and yarns in different parts of a cloth simulation, basically trying to achieve the best performance depending on what you try to simulate in which part of the garment. So first of all, we are going to use non-conforming discretizations for our different discretizations of the simulation. So basically, if we need, for example, to achieve a multi-resolution simulation, we are going to put two meshes that they don't need to serve. Okay, somehow the screen just broke for a moment. So, yeah, so for multi-resolution simulations, we are going to put two meshes that they don't need to serve the vertices. So it's very easy to, no, it's already working, but for some moment it was blue, completely blue. Yeah. And yeah, so they don't need to share vertices, so it's very easy to put one on top of another. And for multidimensional simulations, we are basically going to do the same, but one is going to be a volumetric or a 2D mesh, and the other one is going to be a 1D mesh. So yeah, our work is based on two pillars. First, we are going to describe the kinematics of the two meshes together, and then we will try to find some constraints that allows us to do this efficiently. So let's start with the first part. Let's take a set of points that, well, two sets of points, a coarse set and a fine set, and these are only points. We don't care about the underlying topology, if they are connected or how they are connected. We can describe the fine displacement of the displacement of the fine points based on three terms. Basically, the first two terms are the basic functions and the coarse displacement, the displacement of the coarse points. But that is not enough because you can only reach some displacements. You cannot reach, or you cannot expand all the space of possible displacements for the fine points. So basically, we are going to add another term, the fine displacement or the fine offset displacement, and with that you can already reach all the possible displacement for the fine nodes. But of course, this is not enough. Several displacements can be achieved with different combinations of coarse displacement and fine offsets. So we need to constrain this. And basically, to constrain this, we just want the fine offset to be complementary to the coarse displacement. Basically, we don't want to undo the motion that has been done by the coarse points. By the coarse points. Yeah, we constrain it like that. So to simulate that, well, now we have defined our kinematics. So we want to simulate an object that is defined with those kinematics. So basically, to simulate that, we are going to use an optimization. We are going to, well, we just define kinematic and potential energies, kinetic and potential energies, and we are going to do an optimization with constraints. The issue with this is that doing an optimization with constraints can have some impact on the performance of the simulation, and we don't want to do that. So instead, we are going to embed the constraint directly onto the kinematic definition. And we do this basically projecting or introducing a projection on the fine displacements. So the filter, well, we introduce a filter that projects the offsets into the constraint space. And basically the filter has that formula that only depends on the matrix B. So if the matrix B is constant through the simulation, the filter is going to be constant. And yeah, this way you can perform the simulations. You just apply a Newton-based methods. You compute your equations of motion. You solve it like that. And the issue you have is that your equation is not invertible, but that is not a problem. It's already solved. It was solved already in the 90s by Balapet. So basically, you must use a modified version of the conjugate gradient solver that basically projects the change of the solution into the constraint space. So basically, in each iteration of a conjugate gradient solver, you have to multiply by this filter. So that with this, you can perform simulations. So now I'm going to talk the design goals that we have for our basis functions that are the ones that define the filter. So basically, we have two goals. We want that when we have a rigid body motion on the fine mesh, that rigid body motion must not produce deformations on the coarse mesh. So basically, it must the rigid body motions in the fine mesh must produce a rigid body motion in the coarse mesh only. And also the application of the filter, as I said, to solve, we need to multiply by the filter each iteration of a conjugate gradient solver. So we want this multiplication to be as fast as possible. So yeah, that is our second goal. And to do that, basically, we are going to define basis functions that we call Voronoi basis functions. Basically, what we do is we search for each fine point that here I depicted in blue. We search for the closest coarse point, and basically we set a 1 in that case and 0 otherwise, and that way the matrix V is basically a sparse matrix that for each row it just has a 1 or and the rest are zeros. With this definition for the basis function, the good thing is that the filter, the complex part of the filter, the part that we must invert is just a diagonal matrix. So it's very easy to multiply a vector by this filter because you don't have to do anything in that inverse. But with this, it's not enough if we just apply this naively. When we try to rotate the green bar, it just deforms the 2D paths, and of course, because it deforms, it tries to oppose that rotation, and we can't rotate it. So we have to enforce two conditions for being able to perform rigid body motions. The first condition is met by design. Basically, the translation has to be the translation of all the points. That is already enforced. But the second condition basically says that for each coarse point, it must lie on the Voronoi centroid of the Voronoi region it defines. So basically the coarse point at the rest position must lie on the Voronoi centroid of the region it defines here. So when we do that modification, we can see that the rod bar can rotate because it doesn't deform the square paths. I'm going to show some results now. Some things that we can do with this framework we have described. So we can try to simulate composite materials. So we have an object that is represented by a 2D scene cell, and we embed on that object. We embed two reinforcement, and that make the object to be more stiff. So here we compare both simulations, one without the reinforcement and one with it. Or we can also do complex stuff that will be very difficult to do with, if you don't have a fine mesh, it's very difficult to perform this kind of simulations because you don't have enough nodes to represent the material. Also, we can perform simulations. Here we simulate a shear test and produces the typical wrinkles. But when we put some reinforcements in it, like this will be like a typical carbon fiber material, the wrinkles disappear. Also, we can perform close simulation where we mix triangles and yarns, like we did in 2020. the good thing with this is that the performance is much better because we don't have to invert any matrix when we apply the filter. So well, the simulation runs 2 times faster. And in the same way as tracks, we can also have an animated mesh, and we can, well, a coarse animated mesh that is done by an artist, and we can add wrinkles on top. So yeah, also a bit of comparison. In this simulation, we have modified the number of coarse nodes that we have, and these are the numbers that the percentage of the solver that it takes to just multiply by the filter. So in the case of barycentric basis functions, like we did in previous works, the percentage increases when you increase the number of coarse nodes. But with the Voronoi filters, since you don't have to invert this matrix, the percentage is much lower and mostly constant. And yeah, as conclusions, what we have done a framework to mix non-conforming discretizations. We use Voronoi basis functions that yield an efficient solver. Yeah, with this, we can perform multi-resolution simulations or different dimensionality simulations, or even enhanced coarse simulations or animations. As limitations, well, the regions where you embed the fine mesh are fixed over time. You cannot change them because you will need to recompute the Voronoi partition. And also, we are constrained to use this modified preconjugate condition conjugate gradient solver. You cannot use any other kind of solver because the matrix is not invertible. So things to explore how to improve this. Yeah, if you have any questions. Thank you.
Thank you, Mac. Okay. Do we have questions?
Yeah.
Thanks. Nice work. I have a question about the invertibility. Can you provide more details on what slide?
So basically, F is a projection. So
when it's not invertible.
When it's not invertible, yeah. F basically is a projection. So it's you take some points and you project them to a constraint space. Okay. So F transpose basically takes the points in a constraint space and tries to project them and project them. But of course, there are a lot of possible solutions for that. I mean, from a big space to a smaller space, it's of course just one way, but from a smaller space to a bigger space, there can be several solutions. Yeah, so that is basically why this is not.
This reminds me a little bit about the complement technique.
Sorry?
This is almost like a maybe composition technique where coarse and fine levels of the simulation with essentially like the interface is the nodes of the coarse level. Is my interpretation of that correct? This looks like
I'm actually not sure. We are not moving from one representation to the other. We just solve both at the same time.
Right, but you have constraints.
Yeah, we have constraints, and the constraints basically are what is here, that they have to be complementary. The fine offsets cannot undo what the coarse motion has done. But instead of applying this constraint directly, we embed the constraint on the kinematic definition. So, and that is why we don't need to use a constraint solver, but we have to use a modified version of the conjugate gradient solver.
Thank you.
Okay. if there is no more question, I think we can stop there because Hubert otherwise will be really angry. And thanks. And well, you will have more updated information than I do.
Okay, thank you very much for holding this session. Now, we have a bus that will bring us to somewhere close to the banquet venue. So if you wish to, feel free to pop into the bus. It will leave in 2-3 minutes. Or if you wish to, you can do whatever you want. So, if you wish to join the bus, time is now. Okay, thank you very much.
Don't be late. The bus is leaving at 6:15.